Okay, let us do some numerics for our examples. Example 5. So we have one-dimensional random walk. We should produce the passes of this random walk and compute how much of them stay apart from zero, from the origin, between 50 and 1000 steps. Okay, this is a simple program. I use Delphi, you can write this in Python. But okay, so the step one, this is we produce the output of this function is -1 with the probability 1 over 2 or +1 with the probability 1 over 2. Random is a function which is randomly uniformly distributed from 0 to 1. So if it is less than 1 over 2, then we return -1, otherwise 1. So this is exactly generates the probability 0.5 for the +1 and 0.5 for the -1. Okay, so pass. What is pass? We generate n steps and the output is the sum of these n steps. So this is exactly where we stay after n steps in this random walk, in this simple random walk. Now the function count, which generates n passes, passes, each of which consists of n steps, and compute how much of them stays apart from the origin, from the starting point, between A and B steps. So we exactly compute if this pass between A, M, and B, we add this to the result. So generating n passes, we compute how much of them stay between A and B steps. And now this is for our example, we generate n 10,000 passes with 10,000 steps and compute how much of them stay between 50 and 100 steps and -100 and -50 steps. And after that, we divide this number of counts by the number of the generated passes. This is exactly gives us the probability that random walks stay between 50 and 100 steps. Of course, in the left, it will be between -100 and -50 steps. This is exactly program for this example. And now we will compare this value with 0.3, which gives us the theoretical results. Okay, let us run this test probe AB function. And to see what happens. Yeah, 0.3. Okay, let us run again. Also close to 0.3. Again, 0.3. Let us make, for example, only 1,000 passes and again 10,000 steps. What happens in this case? 0.3. So our theoretical results is confirmed by our test. Next function is for this probability, for the example on the next page, where we produce passes and compute how the growing rate of the Sn, of the length of the pass. it should be something like we should take power 2 and it should grow like n multiplied by the constant c. And we remember from our theoretical result the constant c is exactly 1. Okay, let us check is it really true or not. So this program we generate 10,000 passes with 1,000 steps, compute square power 2 of the length of the passes and compute after that the probability, dividing by the number of generated passes. Let us try to see is it really. And after that we divide by n step to obtain this constant c. You see, if we divide this expectation by n, we obtain exactly this constant c. And this constant c should be equal to 1. This is our theoretical prediction. Let us try to see is it really true or not. This is our program. Okay, yeah, the value is very close to 1. Let us try again. 1. So our constant is computed in the right way. Okay, super. And now more a complex problem. I think this is really good exercise that allows you to understand the probability in the deep level. So what is the constant c in this way? We compute instead of taking power 2 and dividing by n, we just take the modulus and divide by square root of n. We obtain this constant c. We think from the previous, if you take square root, c should be something like 1. Is it really 1 or not? I wrote the program. So we generate we generate 10,000 passes with 10,000 steps. After that, we compute absolute value of the passes and divide by the number of passes. And after that, to obtain the probability, we divide by square root of to obtain the constant, we divide by square root of n. We remember it should be square root of n. If we divide by square root of n, we obtain exactly the constant c. Let us see if it is it constant 1 or not. No, this is not 1. This is 0.79. But maybe, yeah, 0.8. So this is less than 1. And what is this constant? Maybe this is 1 divided by square root of 2, or maybe something else. This is interesting question. So theoretical answer exists. So it's possible to obtain this theoretical value by using central limit theorem. This is exercise to you. But even if you obtain the numerical results, it will be also great. Numerical result not for this example, because I already show you how to obtain this numerical result, but numerical results for this example, where you have 4 steps. And for people who would like to go further to the really advanced understanding of the probability theory, I recommend to do this exercise and obtain numerical results in this both exercises. And the people who are really would like to understand probability theory, for those it would be very nice if they can compute this result analytically and compare with numerical results. Analytical results, it contains some special constants like pi, square root of 2 or something like that. It is not difficult exercise, but it requires some mathematical background. Not big, because in all my slides I already present everything that you need to use to obtain this result analytically. Okay, thanks. Try to do this. Thanks for the attention. Try to do this exercises. They are really very useful.